Hello, my name is Igor and welcome to my Tech Fun. In this video I'm testing three different filaments from eSun, and these filaments are sent to me by eSun for the review. And these are ABS Plus, PA, that's polyamide or nylon, and the third one is PC or polycarbonate. These filaments require a little bit higher temperature. Some informations are on the box already, but some are not. So from their website I collected some main information. The printing temperature for ABS Plus is between 220 and 260 degrees Celsius. The bed temperature is between 90 and 110 degrees Celsius. And in all three cases I will use a glue stick for better adhesion, and they have to be printed inside an enclosure. I'm not sure about the polycarbonate, but I know that the nylon needs to be dried. So it is very important. I will try to print out of the box, but if I will have a lot of stringing, then I have to dry the filament and to print directly from the dryer. For the ABS, it says it is heat and oil resistance, tough, hardness and scratch resistant. For the nylon, the printing temperature is between 230 and 260 degrees Celsius. The bed temperature between 80 and 90 degrees Celsius. High toughness, oil and chemical resistance, and as I mentioned, it has to be dried. And the polycarbonate, the printing temperature is even higher, 235 and 260 degrees Celsius for the nozzle, and 80 to 110 degrees Celsius for the bed, and it is temperature resistant. And I'm very curious if this is maybe a better choice to print 3D printed parts, for example, for the Voron, because the ABS Plus from the eSun is actually the most popular material for printing those plastic parts for the Voron or similar printers. And I'm very curious if maybe a polycarbonate is better solution for this. I know nylon no, so this is good for some other aspect, but I will do my typical experiments with those test specimens which we already saw earlier in different materials, and these results are comparable with each other. But also I want to include here creep test, because here I can see if the material will deform under the constant load during the longer period of time. Let's take a look of the spool. As usual, we have some product manual. And this is the spool. I like this transparent solution, so I always can see how much filament I have on the spool. This is all the information we have on the spool. As you can see, ABS is in white color, the nylon is in this transparent color, and very similar spool, and we have a sticker with the printing temperatures, but no information about the bed temperature. Polycarbonate, and this is half kilogram spool, and here we also have this sticker. And I'm starting with temperature tower, so I can decide on which temperature I will print. Here you can see the modifying of the G code to change the temperature on certain layer position. And this is the compact temperature tower by Izod from Thingiverse. As I mentioned earlier, I'm using a glue stick for better bed adhesion, and inside the enclosure will be approximately 45 degrees Celsius. I'm not sure if you are familiar with printing inside the enclosure. We don't need a high temperature inside. 40-45 degrees Celsius are enough, but what is important that keep it closed and don't open it until it's not finished to prevent any kind of breeze of the cold air over the printed object. This is the last element on 220 degrees Celsius, and inside the enclosure it is 45 degrees Celsius. And it's finished, and it's always like unboxing a gift, opening an enclosure. I can feel that ABS smell, not too strong. It sticks very good, so I wait the surface to cool down and then I will remove it and analyze it and then decide on which temperature I will print. And this is the temperature tower. Let's analyze it a little bit. So there is no stringing at all. That's usually not even the problem with ABS. But the overhang, yes, because a very small part cooling, and this is very bad overhang. And of course the best is on 220 degrees Celsius, but I think these three are quite equal, so probably my choice will be printing on 250 degrees Celsius to get better layer adhesion. And you can see the bridging is also very similar in all 5 cases. Well, the next printing will be the test specimens, and it will be 4.5 hours printing. All ABS parts are printed, ready for testing. And it's time to test polycarbonate. And as you can see, this is half kilogram spool. The nozzle is on 240 degrees Celsius and I can feel quite big resistance when I push with my hand. So yes, definitely this is the lowest temperature which I will try to print this filament. But of course the temperature tower will always start from the highest temperature. The first layer goes down perfectly, and at the end of first element I can see the only problem with some warping on one of the corners. It had a really nice progress, so I left it here and it was quite easy to remove it when it's cooled down. Let's take a closer look. And here it is. It looks really good, much better than the ABS. The overhang is perfect, the bridging too. The only problem I can see that on 240 degrees Celsius this candle for stringing test was broken. I'm not sure what resulted this because I wasn't here to supervise it. I was quite sure that it will be printed correctly after I saw the first 2 elements. So I print everything on 250 degrees Celsius. And the last group of test specimens from polycarbonate. First I wanted to print all test specimens at once, but this one for the bending test curled up and the nozzle hit the object and it removed through the bed, so I decided to print all test specimens one by one. And what was my solution for that bending test specimen? A Kapton tape. Not too elegant solution, but it works. So I designed here a 2-layer thickness, additional, let's say, brim, but this is part of the design. And then I glue it with the Kapton tape after it was printed. I already did something similar, just placing a flat magnet on my Prusa Max 3S because it has magnetic surface, but here I cannot use magnets. Well, not too elegant solution, but it worked. And it's completely straight and it's easy to cut it off because it's only 2 layers. It's time to print the nylon, and I will try to use it out of the box and I will not dry it, but you should know that nylon, beside the enclosure, it needs to be dried also. But inside the enclosure, if the temperature is higher, then it's a little bit dry environment, so well, I will see how it performs. Wow, I cannot hear any crack sounds, so the nylon is dried, but look, those corners, they curl up, so the warping is very big. Oh, I will have problems with printing the test specimens. Currently in enclosure it is 40 degrees Celsius. Probably it needs more. And after second element, it removed from the bed. Now actually the brim stick good to the bed, so the bed adhesion is good, only this warping is so big that even with big bed adhesion, it curls up and removed from the bed. But two elements are printed, and yes, I have some stringing, but the overhang came out perfectly, and also the bridging, even on 260 degrees Celsius. The problem is this warping, so probably have to raise the temperature inside the enclosure. And actually, I don't know, maybe add a little bit more glue stick. I don't have other ideas. So this is the temperature tower from 240 to 230, and this one which failed was between 260 and 250. So definitely a lower temperature helps against the warping, but far from perfect. But for better mechanical strength, I will print everything on 250 degrees Celsius. One by one each specimen. First test specimen printing is almost finished. Even with the Kapton tape it is very hard to hold it down. And temperature inside the enclosure is 46 degrees Celsius. And you can see even with the Kapton tape it was very hard to hold it down. So definitely not problem with the adhesion. Very hard for printing. Definitely needs bigger, higher temperature inside the enclosure. You see, very good adhesion with the brim. I paused the printing. I recorded this just to demonstrate you my Kapton tape method. But look the adhesion, and this was not enough. Yes, crazy solutions, but at least they work. And the last nylon object. Hygroscopic filaments I store in vacuum bags, and this system I got from the iBoss. There, all test specimens are printed now, and before I start with mechanical testing, first a quick overview of the printing. Actually, the easiest for the printing was the ABS. The only problem I had with the overhang. The next one was the PC or polycarbonate. Here the only problem I had is with the warping on some elements. For example, you saw this for the bending test, but everything else was quite good. Even better overhang compared to the ABS. And the hardest for printing was the nylon or PA, polyamide. Biggest problem was the warping. I thought the biggest problem would be the wet filament, but it was completely dry. I didn't hear any crack sounds or something like that. So this was dry filament. I could get a very good adhesion to the bed, but even that you saw it has a lot of warping. So definitely for printing nylon it needs a bigger environment temperature. My biggest was 46 degrees Celsius inside the enclosure, so probably it requires maybe even 50 or 55, but sometimes that is too much for the electronics, so it really needs some special printers for this. As you can see, ABS is in white color, but PC and nylon are very similar in this some kind of transparent color. So I marked the PC test specimens with this red line, just in case it's easier to follow on the cameras. And I'm starting with the tensile test. These test specimens are printed in horizontal position. The smallest cross-section area is 4 by 4 millimeters. And they broke on very similar load. And this reminds me on the weaker layer adhesion. Next one is the polycarbonate. And they broke on very similar load and exactly on that smaller cross-section area. Nylon. And the nylon also broke on the smaller cross-section area. This is how they broke, and this type of breaking makes me think that it has a little bit weaker layer adhesion, but it will be tested in my next experiment. The results I will show you in a summary later in this video. The next experiment is the layer adhesion test, and again the smaller cross-section area is 4 by 4 millimeters, and I'm starting with ABS. Then the next is the polycarbonate. I was expecting a little bit bigger layer adhesion here. And then the nylon, and here I was really surprised. It was extremely strong, it was very hard to break it with my hand. And this is how they broke, exactly on those smaller cross-section area. This is ABS, polycarbonate and nylon. ABS. And the next experiment is the bending test based on ISO 178. And I'm recording the load at 2 mm deformation, maximal load and deformation on the maximal load signs. They didn't broke. Next one is the polycarbonate. Distance between supports is 50 mm. And you will see from the numbers very similar results like with the ABS. And the next one was the nylon. And actually on this test it acts very similar like ABS and polycarbonate. And as you can see, none of the test specimens broke, so they just deform. And the next mechanical test is the shear stress. And the diameter of these test specimens is 5 mm, but the area is doubled, and I'm starting with ABS. And it broke on exactly 3 parts. And the next one is polycarbonate. It just exploded, but it also broke on 3 equal pieces, only I couldn't find one. And then the nylon. And this was really strong. ABS, polycarbonate and nylon, and they broke exactly how they should do on those 2 cross-section areas. They are shared. And here I missed one piece because I couldn't find it. With this Izod impact test I can see which of 3 materials is more brittle. And actually the winner in this test is a good choice, for example, for a bumpers on RC car or something like that. So I have here half kilogram hammer, and it will swing to the other side. That will be the 0 position. And after I placing here the test specimen, it will break it and swing to the lower position, and from difference in height I can know how much energy is used to break this test specimen. ABS. Opa. It didn't broke. First time in this test. eSun ABS Plus. Very impressive. Polycarbonate. The 0 position. Nylon. So this is the scale, and this is the 0 position of the hammer. And this is the position of the hammer after breaking the PC test specimen. And this is after breaking the nylon. And just to remind us, the ABS Plus didn't broke at all. And if I measure everything for the 0 position, with this equation I can calculate the breaking energy. In this torque or twist test, I have this 6 mm in diameter cylindrical part. The length is 22 mm, and this side goes into the vise and the other side goes into this torque meter. And I want to record the load at 90-degree angle, the maximal load, and maybe the maximal deformation. I'm starting with ABS. Already broke 1.1 Newton meters. Yes, and that was the peak too. The next one is polycarbonate. Again, I heard some crack. 1.7 was the peak so far. And the nylon. .9 is the peak so far, and it doesn't really break yet, it's more like elastic. ABS broke quite quickly. Similar was the polycarbonate, and as you can see, this is sign of the weaker layer adhesion, and that's what we saw in that experiment. And nylon, it didn't actually broke, and here I could make maybe almost 2 twists until I feel it's deformed, but it didn't broke at all. I will measure the hardness with this short D durometer, and knowing the hardness, maybe we can know how scratch resistant is some material or something like that. And I will measure all these bending test specimens in perpendicular to the layer direction. .69, 69.5, polycarbonate, 75.5. Smaller values means softer material, and here I also noticed creeping of the nylon because it needed approximately 3 seconds to stabilize the penetration of the needle. In this experiment I want to record the temperature at the first deformations. I have here ABS, polycarbonate and nylon, and M10 nut as a small load on each test specimen, and I will measure the temperature with this thermometer. Soon I will change the method of this temperature test. I will follow the ISO 75 standard, but this is comparison test anyway, and there was no surprises in the order for me, only I wasn't sure about the exact values, so the order was the ABS, PC, and the highest temperature resistant was the nylon. We stop the experiment now on 186 degrees Celsius. And this is the result. ABS, polycarbonate and very impressive nylon. One last closer look when they cool down. So this is the ABS, and this is very interesting. The polycarbonate, I can still see this red line. And this is nylon, very impressive. I'm starting with preparing a creep test because it will take 7 days. And what is important, the distance between these two surfaces is exactly 12 millimeters. And more about this test you can see in my first creep test video. So this is the ABS, then the polycarbonate and the nylon. And I am adding this 1.25 kilogram load. And I will measure the deformation. I will log the position of this test specimen and I will measure the distance between those two surfaces. 20.77. The polycarbonate 16.56 and ABS 16.05. And this is the position after a little bit more than 24 hours. And I will not show every time the measuring, only one more time maybe. 33.76, 16.74, 16.64. And after 2 days I can see that the nylon is continuously creeping until the polycarbonate and ABS, visually I cannot see big difference. Interesting situation I have here on day 3. Of course nylon creeps continuously, but visually I can see now the ABS plus is more deformated than the polycarbonate, but it was the opposite a few days ago. And this is the position after day 4. And this is the position after 5th day. And now I will put these test specimens into enclosure on 45 degrees for 1 hour, and then I will measure it again. I could heat up the temperature to 48 degrees Celsius in less than 5 minutes. So now I will left it here 1 hour and then I will measure again the creep. There are two my strongest filament dries, the Creality and iBoss, works on AC power, and then we keep the temperature on probably on 45 degrees Celsius. Oh, it went up to 49. And 1 hour almost passed and the temperature went up to 80 degrees Celsius, and now I will stop it and measure all the test specimens and then show you the results and then conclusions. And this is how they look like after 1 hour on 48 degrees Celsius. I will measure them now and show you all the results and then conclusions. And now I can take off the load. And also I'm preparing the second type of the creep test, also presented in that first creep test video. So this is M5 bolt and M5 nuts from the other side, which will be placed in this vase. The vase only holds the nuts, and I will tie these bolts with the torque meter. And tomorrow I will see if I can additionally tie the bolts using the same torque, and of course I will measure the angle of the additional rotation. And now let's see after 1 day how much I can tighten more these bolts. Hardly move something. It didn't move. Didn't move. Didn't move. 5 degrees. Didn't move. Maybe 1 degree. Ten degrees. Nylon after heating. The average. And here you can see all the results on one place. You can download this Excel from my website. And let's see maybe the graph, it's more interesting. So this is the creep test. This is a deformation of that C test specimen. And it started from 12 millimeters, and as you can see the ABS and polycarbonate almost didn't creep at all until the nylon had a continuous creep, and even here the last point is after placing in an enclosure on 48 degrees Celsius. And this is that screw creep test, rotation angle after applying the same torque, and the perfect is 0. So here we can see that after maybe 2 or 3 days the ABS and PC don't creep at all until the nylon continuously creeping, even here, and especially after placing inside the enclosure on 48 degrees Celsius. This means if you use, for example, ABS or PC for some printed parts or something like that, when you tie the bolts, check them maybe after 1 or 2 days, tie them a little bit more, and then they will be fine. Tensile test, no significant difference here until the layer adhesion test. These two, ABS and PC, was quite disappointing until the nylon really impressed me. So this is quite big for the layer adhesion test. This scale is 200 kilograms, so we can compare them. But shear stress, I don't think it is too important for these applications. And here you can see the bending test. Interesting, all three materials act very similarly in this test. And this was very impressive, the impact test, and this is just for reference actually, because the ABS Plus didn't even broke. And even the nylon performed quite good in this experiment, and the polycarbonate was quite brittle actually. And this is the torque test. I don't know, maybe I wouldn't say that it's a significant difference. And this is the deformation temperature test. This is not standard, soon I will start with the ISO 75 following that standard. But anyway, this is comparison test and something like what I expected. But I was surprised a little bit with this nylon, how good perform here. Until it creeps under constant load, interesting. And this is the hardness, very similar values here. And now the conclusions. Well, first of all, I think I have too many tests. Maybe I should reduce, I don't know, maybe drop out the shear stress or something like that. Because I usually feel that I scare people with half-hour material review video. Well, anyway, about these three materials, as you can see, there is no straight answer which of these three is the best. Depends on your application. For example, I was very impressed with the impact strength of the ABS Plus material. But was disappointed about weak layer adhesion. Similar with the polycarbonate, it has a better temperature resistance. And about the nylon, it's a pity that I have that very big problem with the warping, because I was really impressed with that layer adhesion. Well, maybe this means I can reduce a little bit the printing temperature, and this gives me chance for better printing. In near future I want to test different layer adhesives to the bed, and I read about Magic Glue. I want to buy this set. It costs approximately $100, so this means I have to collect 2 months donations for the Patreons, because as I promised, usually I spend all Patreon donations to different equipment on this YouTube channel. Well, anyway, I will see. If you have any additional information or suggestions about these materials, please let me a line in a comment. Thank you for watching and happy printing!